We continue to learn Chapter 1, Matrices and Systems of Equations. Section 3 about matrix algebra. In this part, we will learn about identity matrix and inverse matrix. For any n by n matrix A, we try to find a matrix that acts as an identity for matrix multiplication. So this matrix times matrix A equals A times this matrix equals A. In order to have this relation, we can define the n by n identity matrix like this. The identity matrix equals delta ij, where this entry ij entry equals 1 if I equals j, 0 otherwise. So the identity matrix is just a matrix with main diagonal entries all 1 and other entries to be 0. The column vectors of n by n identity matrix I are the standard vectors used to define a coordinate system in Euclidean space. See, for example, in 2 dimensions, if you have 2 axes, right? In order to represent a vector in 2 dimensions, no real vector space, then you just need the axis in 1, 0, this vector, and 0, 1, this vector in the x2 axis. E1 equals 1, 0 in the x1 axis. You can represent this point, this vector. Okay. And now we consider about matrix inversion. An n by n matrix A is said to be non-singular or invertible if there exists a matrix B such that A times B equals B times A equals identity matrix. The matrix B is said to be the multiplicative inverse of the matrix A, and we denote it by A minus 1. Okay, this is the inverse matrix. An n by n matrix is said to be singular if it doesn't have such a multiplicative inverse. And we have this property. A matrix can have at most one multiplicative inverse, or a non-singular matrix has a unique multiplicative inverse. So the inverse matrix is unique. We can show in this way. If B and C are both inverse of A, then we have B equals B times identity matrix equals B times A times C. And because for multiplication, matrix multiplication, you can do any 2 matrices, the multiplication of any 2 matrices first. So it equals B times A times C. And B times A is just identity matrix because B is an inverse of A. And then it equals I times C. Because I is identity matrix, so I times C is just C. So we show that B equals C. Okay, so any matrix, if it is invertible, then the inverse matrix is unique. Now we have this theorem. If A and B are non-singular n by n matrices, then AB is also non-singular, and AB inverse equals B inverse times A inverse. So here we emphasize that for the inverse of the multiplication of matrix, it equals the inverse of matrix, then do multiplication. However, the order must be backward. So AB inverse equals B inverse first, then times A inverse. Okay, we can show this easily because you can show B inverse times A inverse times AB equals you first combine A inverse A first, right? Then you get B inverse times B. B inverse times B, by the definition, it is identity matrix. And similarly, you can also compute AB times B inverse A inverse. Okay, you will find it's also identity matrix. So this means B inverse A inverse is the inverse matrix of AB. Okay. And how do you prove the above theorem for arbitrarily given n matrices? This means, for example, A1, A2 till AN inverse should be AN inverse first, then times AN minus 1 inverse times A1 inverse. So also means the inverse of the matrix multiplication equals the inverse matrix first and then do the multiplication. However, the order should be backward. Okay, so you can also use the mathematical induction. First, when n equals 2, this is shown already, right? And then the induction step, assuming true for n equals k, we prove it is also true for n equals k plus 1. Then we finish this proof for this theorem. You can try later.